Would you guys agree? I want to do a question. I think it was 11 in the homework. Would you agree that once I get beyond 4 segments, that these regular polygons all kind of look the same? Okay, it just looks like they're opening up more and more, right? Okay. So when we do a question like number 11, which says, let's see here. Bear with me. All right, so question 11 says that you have an exterior angle of a regular polygon given below. So the exterior angle is 18 degrees. Okay. Find the measure of the interior angle. I don't know how many sides my polygon has. Okay. But would you guys all agree that no matter how many sides it has, it's going to kind of look something like that? Does that make sense? Okay. So when I do these problems, and I just want to make sure we're all on the same page with my drawings here, I am only going to draw like something like that. Does that make sense? Just a I don't know what the rest of that polygon looks like down here. I'm just drawing a portion of it. Okay? But this is saying that the exterior angle is 18. So that angle right there is 18. But if it's regular, what's that angle right there? 18, and that one is 18. Okay. So what is the relationship between that angle of 18 and that angle right there? Supplementary. They're a linear pair. Good. So what is that blue angle going to be? 162. Okay. Now, you have an option on how to solve for this last part. We need to know n. That's the number of sides, right? Well, this 162, an interior angle measurement, can be found using this formula that incorporates n. Excuse me. Now, that's a pain in the butt to do. You can do it. It's not too bad. You should know the algebra, okay? Or have the skills at least to manipulate that algebra. But there's an easier way. What do these 18s all, I don't know how many I have, but what do they all need to add to? 360. So you could do this. You go 18 plus 18 plus 18 all the way down until that gives you 360, and then go back through and count those 18s, right? What's an easier way? Okay, to divide, take 360. If I divide 360 by the 18, it will tell me how many 18s are in that list, right? So 360 divided by 18 is? What's 36 divided by 18? Okay, so this is going to be 20. Okay, I didn't hear you guys. So make sure we can do that, okay? Before you get to class tomorrow, make sure you know your vocabulary. Convex, concave, polygon, regular, equiangular, equilateral, all that stuff. Make sure it's your... Huh? No, just this chapter.
We didn't learn about... Yeah, we didn't. We didn't learn about 8.
Do you guys have any questions on the homework? Anything else on that?
Dang, what's supposed to be seat? It's a little chilly.
If you do, let me know at some point and we can go over them. But let's start section 6.2. Huh? Yes.
How do you do, like, if you were to, because I thought you said something about when you have, like, the n minus 2 times 180 divided by n, you can, like, multiply by n and do all that. How do you do that? Because I got, like, n to the third, to the 120, to the second, and I'm like, nope, and I ended up just guessing and checking you got it right.
All right, so if we use that last one, it was, would have been n minus 2 times 180 over n, right? And we said it was 162. All right, so when we have something like this, we don't, it's called a rational equation because we got ratios. We like to multiply by the least common denominator. Okay, so we multiply by, the least common denominator is going to be that denominator times that one, right? So it's going to be n. So we multiply everything by n. And so this is what happens when we do this. And I'll go through the kind of extended version of this. You get n minus 2 times 180 times n, right? When I multiply that n through the top, all over n equals 162 times n. Now, I didn't effectively, the way I wrote it, didn't get rid of the n, right? Okay? But we can rewrite this on the left-hand side as n minus 2 times 180 over n times n over, I don't want to write that way. Let's not write that way. Let's go n minus 2 times 180 over 1 times n over n. If we use our rules of multiplication with fractions, does that thing still give me that thing? Well, we will, but do you see how that cancels there? That just gives me 1. So what happens a lot of times is that when we write this, we just instantly cancel those. And it's because we could use our commutative and associative properties to recognize that that's just an n over n, which is a factor of 1. So now I have n minus 2 times 180 equals 162n. And at this point, because there's 180 n's over here, and I need to be able to see those, I have to distribute that 180. So it gives me 180n minus 360 is equal to 162n. Now subtract, doesn't matter which way you go here. I'll get negative 360 equals negative 18 n's, and then 360 divided by 18 will give me my n. Does that make sense? There is another thing of algebra that you could do here. Now, it doesn't make sense with this one, but because these two things are multiplied together, okay, can I divide before I distribute? Can I do this? Can I say 180 is equal to 162 over n divided by n minus 2? Okay, so you've got, when you see something like this in general, you've got options. You can either distribute, okay, or you can divide, okay, and get that 180 by itself. Now, dividing here doesn't make a whole lot of sense because now, what do I do here? Okay, or you could take n minus 2 is equal to 162n over 180 and do it that way, and now try to move that n over here with it and solve that way. Those aren't very, they're options, but they're not very, or they're not, I guess, as effective as distributing is. Does that make sense to everybody? Okay, so I think it's important to understand what your options are when you're doing your algebra, but also understand of those 2 or 3 options, which one's most efficient for this type of problem. And distribute that 180 through is the best route. Moving on to 6.2, guys, and there are some videos online under 6.1 that show you how to do that formula again. I want to talk about the structure of this course a little bit. You don't have to draw this down. Don't write this down. I'll give you a better kind of diagram later on in the chapter. But one aspect of Euclidean geometry is investigate two-dimensional shapes. We've investigated kind of our undefined terms, our lines, our rays, our points, in our planes. And once we've done that, we kind of start pushing those and merging those together, okay, using multiple segments, multiple rays, multiple angles, multiple points, and we end up getting shapes. And the first shape that we found was a triangle, right? Or the first polygon we found was a triangle. And we learned a lot about triangles, okay? So Euclidean geometry is an investigation of those undefined terms to create polygons. And of those polygons, we get triangles. Now, if you remember back to what we did with triangles, we did a lot with triangles, right? Okay, but in regards to the shapes, we talked about like isosceles triangles, we talked about scalene, we talked about right triangles, and then there's a list that goes on and on, right acute, right obtuse, that kind of stuff, right? And we also have the ability to say, okay, is an isosceles triangle ever going to be scalene? Can't, right? But is an isosceles triangle, maybe could it be right? So maybe we can link those together and create kind of a web of ideas over here with triangles. Does that make sense? And relationships. And that's what a lot of chapter 4 and 5 was about. Okay? Today, we're going to start talking about quadrilaterals. How many sides are there in quadrilaterals? 4. Okay? Now, the main quadrilaterals that we're focusing on today are going to be parallelograms. Okay? And we're going to learn the features that distinguish a quadrilateral and a parallelogram, or it makes a parallelogram a little bit more special than just a generic quadrilateral. Does that make sense? It's like when we were in triangles and we say, well, what are the features that make an isosceles triangle different than just an arbitrary triangle, right? And it was the congruent sides, right? Okay? So when we talk about parallelograms, there's going to be a feature that distinguishes them from just any other four-sided figure. Okay? But there are also some features of parallelograms that distinguish them and make them a little bit more special. And there's a feature that makes them a rhombus. There's a feature that makes parallelograms rectangles. Those two features working together at the same time get us squares. Okay? So we're going to investigate it, and it's going to take a couple days today all we're going to talk about is parallelograms. And in the next couple days, we'll focus in, hone on those ideas and concepts and get those ingrained in our minds, and then we'll start to add to it. Okay, if I start with a parallelogram and I add this one characteristic, does it make it a rhombus? Does it make a rectangle? Okay, and then we start to see the differences that those shapes have in comparison to just generic, regular parallelograms. Does that make sense, everybody? Okay. Once we're done doing that, we will look at another type of quadrilateral, which is called a kite. And we're done with those. We'll talk about trapezoids. Come on. There we go. And we talk about trapezoids. There's going to be a couple different types of trapezoids. We talk about isosceles trapezoids, talk about right trapezoids, that kind of stuff. But then eventually, once we know that, we're going to say, okay, a subgroup of polygons again is your regular polygons. And those are your hexagons, octagons, heptagons, decagons that all have equal angular and equilateral sides, right? And what we'll find out is if I can learn something about a hexagon, a regular hexagon, there are very, very, very similar features for a regular heptagon. Very, very, very similar features for a regular octagon. Does that make sense? So we start to investigate these groupings and subgroupings of polygons. Okay? Once we do that, once we learn about everything in two-dimensional renderings, okay, just in basically the XY plane, we then say, okay, what if I take a bunch of these things? What if I take maybe a trapezoid and let that be a base of a three-dimensional shape, and I then take maybe rectangles and let those be the sides of my three-dimensional shape, or my faces of my three-dimensional shape, and I create this trapezoidal prism. What can I use, or what features can I figure out about this trapezoidal prism, like volume and area, or surface area, and how can I determine that stuff based off what we've already learned about two-dimensional trapezoids and two-dimensional rectangles? Does that make sense? Okay. So as we move on through the year, the last couple chapters of the year are surface area and volume of three-dimensional shapes. In order to be successful at that, we have to have a very good understanding of our two-dimensional shapes, because those are what go together, or pieced together, to create the three-dimensional shapes. Okay? A lot of our area formulas and a lot of our volume formulas have a foundation in regards to our two-dimensional shapes in the properties that we're going to learn in the next couple days. Okay? Today we're going to hone in on parallelograms. Okay? Parallelograms are a special type of quadrilateral. There is something that distinguishes them from other basic generic quadrilaterals. When I say quadrilateral, what should come to mind is anything that looks like this shape here. And you can change it and make it anything you want, okay? That's a quadrilateral. What's the definition of quadrilateral? Four-sided polygon, right? Is that? Yeah, okay. But is that also a four-sided polygon? Yeah, okay, so that is a quadrilateral as well. Okay, now, eventually, we're going to get to that thing. Is that a four-sided figure? Absolutely. But there is something about that one that is different than all the other ones that I drew that are going to make it special, that distinguishes it. Okay? And the one that is, or the feature that's different there, or unique, is that our sides are parallel. Okay? So a parallelogram, that's the first definition I want you guys to write down today. Parallelogram. Quadrilateral with both pairs of opposite sides parallel. Both pairs of opposite sides parallel. Getting cold in here, ain't it?
A little bit.
We were working in the two-dimensional plane, the XY axis. So put my axes in here. Okay? What is the feature that we use to determine whether lines or segments are parallel to one another? If they have the same slope. So if I look at these purple lines here, they both have a slope of 3/2 or 1.5, right? And no matter where I move these vertices, we see that these two slopes are always the same to one another. Is that all right with everybody? So that's one set of opposite sides. Now I'm just showing you the purple ones, but if I were to show you the slope of the blue ones, are those the same? Okay. So what's going to happen here, and what I think is really interesting about this course is that we have already learned everything that all the information that we need to create the rest of Euclidean geometry. In chapter 1, 2, 3, we laid the foundation for the rest of the course. Okay? Now all we're doing is taking those components and those ideas and putting them together, okay, to create new ideas and new concepts. What we've already done in chapters 1, 2, 3, 4 is we worked in the coordinate plane with the distance formula and the slope formula, right? We're going to come back to that. We're going to ask you, I'm going to give you 4 points. I'm going to ask you, is this thing a parallelogram? Well, what do we just see visually that we have to do to see if a shape is a parallelogram? We have to find the slopes, right? Find all 4 slopes and then compare them to see if the opposite ones are the same. And then that can be enough to prove that you have a parallelogram. Is that all right? Okay. That's the main characteristic that distinguishes that shape from any other just generic quadrilateral. Okay, so if I just have that blue quadrilateral, okay, it is just a quadrilateral. It doesn't have any unique behaviors that distinguish it. Okay, but the one on the maroon one there, the one with the blue sides and purple sides, that has a unique feature. That's a parallelogram. Okay, everyone? Okay. So now we've got some properties. And these properties are all expressed through theorems, meaning that we can prove these, meaning that we will prove these. Okay. If I do this tomorrow, I want to kind of lay them all out for you today so you can mess around with them, do the homework assignment, and then tomorrow we'll come back and talk about why. Okay? Yes?
Is it on the tests and stuff, is there going to be like what theorem is it?
I mean, there's going to be pictures. Like I will give you eventually like a picture like this and ask you, is there enough information there to tell me that that's a parallelogram or not? and in this case, because I've got the parallel sides and everything, that you could say yes. But I mean, I'm not going to have you write out or have to identify the opposite sides of parallelogram are congruent, but you're going to have to use and apply that theorem. So this theorem says opposite sides of parallelogram are congruent. So I get those blue segments to be congruent, and I get these red segments to be congruent. And this is kind of a point, I think, in the year that we need to talk about our theorems and taking the information from our theorem and using just that information. Does it say that all four sides are congruent? No. Okay? It just says opposite sides are congruent. Okay? Does that eliminate the possibility that all four sides could be congruent? No, because if I had, let's say, let me just show you a picture here real quick. All right, so there we're seeing that opposite sides, and they're using the distance formula, so using the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared to find these lengths. There we're seeing that the opposite purple sides are congruent and the opposite blue sides are congruent, right? That theorem doesn't say anything about the fact that all four sides could be congruent. Give me a shape of something that could be all four sides be congruent. Okay, so you guys know squares, right? So there we go. So there we see that we get all three sides to be all four sides, 5, 5, 5, right? Now, does that theorem still hold, though? Are both pairs of opposite sides still congruent? Are those two congruent? Are those two congruent? Yes, okay? But because it just says both pairs of opposite sides are congruent, that is still a parallelogram. Okay, does that make sense? When this happens, that's a special parallelogram. That's a characteristic that allows us to go down a little bit further on that flow chart to in this case, because there's some other things going on, this could be a square. But what if I did this? I can never remember which points I'm allowed to, I think point D I can't move. Is that a square? Make it more drastic. Is that a square? Or is that, that's not even, I need to go one more. Okay. So that's not a square, right? Okay, those angles are not 90-degree angles. What, in GeoGrip, it looks like a 90-degree angle. It's a 90-degree angle. Okay. So none of those angles look like 90-degree angles. So, but we do have both pairs of opposite sides congruent, right? And in reality, we have all four sides congruent, correct? Okay. Then we know what that is called?
Equilateral, quadrilateral.
Okay, it's an equilateral, quadrilateral. What's a better name for that? It's a rhombus. Okay. So that's the feature that distinguishes a rhombus, and it's based off the definition of what a rhombus is. That is the feature that distinguishes it from any just generic parallelogram. Does that make sense? Okay? So when I tell you guys to imagine a parallelogram, or we're working with a parallelogram, I don't want you to think about a rhombus. I don't want you to think about that shape. I want you to think about maybe something like that. Okay? Something that is not a rhombus, something that's not a rectangle, something that's not a square. It's just a general, generic parallelogram. Does that make sense? If I want you to think about a rhombus, I will say think about a rhombus. Okay? So those are some properties that are important to us. If we look at the opposite set of angles here, so look at angle D and angle A. What do you think the argument is going to be about angle D compared to angle A? Yeah, they're going to be the same. 43.48 and 43.48. No matter where I move these points and create a different parallelogram, Are those angles, those green angles, the same? And if I look at those red ones, are those red ones the same? Yeah, okay. So our second theorem, our second relationship is that opposite angles of a parallelogram are congruent. Opposite meaning that they are non-consecutive. You have to go from one to the other opposite angle. You have to pass through the interior of your polygon. I like talking about, you see in the PowerPoint, I skipped a couple slides to get to this theorem. There's proofs of these theorems, right? Okay. Think about the number one property that's existing with parallelograms is that you have parallel lines, right? Chapter 3, did we do a lot of proofs about parallel lines? Alternate interior, alternate exterior, same side interior, that kind of stuff corresponding? Okay. Well, if I've got parallel lines in this polygon, I probably have some same side interior angles, maybe some alternate interior, that kind of stuff, right? Okay. In chapter 4, did we deal with proofs of triangles? Same side, or sorry, side, side angle, that kind of stuff, right? Okay. Well, in this picture here, in the last theorem as well, if that is parallel to that, and that is parallel to that, you have a bunch of parallel lines. So we can start talking about our alternate interior, alternate exterior, same side interior angle proofs. If I draw that diagonal, what did I just create in my parallelogram? Two triangles. What do you think you're going to know about those two triangles? They're congruent. Okay? So if I can use, and the way that I showed those two triangles are congruent is through the use of the parallel lines, because look at this angle right here. That angle there and that angle there are what to one another? They're alternate interior, so they got to be congruent, right? Okay? Is this side right here congruent to itself? Because it's a parallelogram, provided the last theorem is true, is that side there congruent to that side there? Are those two triangles congruent by side angle side then? So then by CP, CTC, the remaining angles that we haven't talked about are also congruent. Does that make sense? And one set of remaining angles would be the opposite angles in the parallelogram. So when we go through and prove this stuff, we already have done the proofs. We've just done them separately. We did part of the proof in chapter 3, and we did part of this proof in chapter 4. In chapter 6, we just slammed those two things together. Does that make sense? Okay? So that's the idea. As we move through the course, guys, that's the idea. When we learn something new, it's bridging old information together to create something new. All right? So opposite angles of a parallelogram are congruent. What do you think you know about, if I were to take that angle right there and slide it over here? What would you tell me about that red angle and that blue angle if they're together over here like this? They're linear pairs, so they're supplementary, right? So what do you tell me about them in that position to one another right there? Supplementary right there, correct? Now, what would you name those angles as in regards to the location? Okay, so they're supplementary because they are indeed same side interior. And we'll talk about that in a moment. But what would you call them in regards to their location to one another in the polygon, in the quadrilateral? Consecutive. Okay? Those are consecutive angles. Okay? Same thing with these two, right? Can I move that blue one up there and these two up here be a linear pair? Can I move this red one up here and those two be a linear pair? Okay? So then back into their normal positions, those consecutive angles, okay, that blue one and this red one, or this blue one and this one up here, have to be supplementary, right? Okay? So that theorem stated right here, consecutive angles in a parallelogram are supplementary. Consecutive angles in a parallelogram are supplementary. And Kenny said the reason why, okay, is if this is a parallelogram, what do you know about that side compared to that side if it's a parallelogram? By definition, they are parallel. What is that for those blue parallel lines? Transversal. Therefore, this angle here and that angle there are same side interior, right? And same side interior angles have to be supplementary. And if I just erase the parallel lines and the transversal, are those two angles consecutive inside my parallelogram? Okay, so we get consecutive angles in a parallelogram to be supplementary. Now there's 4 sets of consecutive angles. There's those two. My computer is on the fritz here. Come on. All right. So that is a set of consecutive angles, right? Those are a set of consecutive angles. And those are developed by looking at the side, the left and the right being parallel. But can we look at the top and bottom being parallel? So that line and that line are parallel. And that would be a transversal, right? So is that angle there and that angle there supplementary? All right, so supplementary, supplementary. And then for the same reason, these two over here are supplementary. Does that make sense, everybody? Okay, so consecutive angles in a parallelogram, and here's just one set of them. As I move those around, obviously you see the numerical values of those angles, their measurements changing, right? But does the sum of 180 ever change? Nope. I can do the same thing for this set. Move those around. The two individual parts change, but the sum never changes from 180. Okay? So something we can do? All right. This is the last one. The next theorem has to do with diagonals. Now I'm going to make my parallelogram obscure. I'm going to make it very kind of shallow or skinny, yeah. Because my question is, when I look at those diagonals right there, those black dotted lines, are they congruent? Those dotted lines are congruent? The dotted lines themselves are not congruent. So if I were to, let's just color them. I look at that red dotted line compared to that green dotted line. They are not congruent, right? Okay, obviously the red one is a lot bigger. Now, could they ever be congruent? What type of shape, what kind of parallelogram do you think they would be congruent in? Okay, rectangle. Some of you said square. Is that going to work? Are they congruent in a square? Yeah, do you know why? Because the fact of these diagonals being congruent is a property that distinguishes a rectangle from other parallelograms. And what is a square? A square is a rectangle. So it does work in a rectangle. Rectangle and a square. Does it work? Somebody said, what about a rhombus? If I asked to let's look at the opposite side lengths here. Let's see if we can make this a rhombus real quick. So that's a rhombus. Does the green diagonal look the same length as the red one? No. Okay, and you can see here that the red one is 4 blocks wide, right? The green one is only 2 blocks. Okay, I don't know what the scale is right now, but so your diagonal for a parallelogram, because we haven't had a theorem yet that says this, a parallelogram, you know nothing about the total length of the diagonals. However, what does it look like the diagonals are doing to one another here in this parallelogram? They're intersecting each other, right? How are they intersecting each other? Okay, so in a rhombus, that's special. Let's look at this one. Is that a right angle there? Look at these distances. So those distances right there are the green ones. So if IB and CI are both 5.59, I is a what? Careful, I is a midpoint. I is a midpoint of that green line, right? So then the red line, the red diagonal is a bisector, okay? Now, it's not perpendicular, right? Okay, so it's just a bisector. So the red diagonal bisects the green one. What about this? What if I look at the red parts, ID and AI? I is now a midpoint of the red one, right? Does the green one bisect the red one? All right, so the way we phrase this then is that the diagonals of a parallelogram bisect each other. Diagonals of a parallelogram bisect each other. Now, we don't have anything that says that our diagonals have to be congruent. They can be, but in general, in a parallelogram, if that's all I know that I have, I don't know if it's a special parallelogram, just a generic, general parallelogram, we know nothing about their total values or total lengths, but we do know something about the relationship between them as being bisecting one another. Okay? When we do know features about their total lengths, the diagonal's total lengths, that is going to be a characteristic that allows us to differentiate a parallelogram and a rectangle. Okay. Questions on that stuff? So there's like 5 things here. Parallelogram. Both pairs of opposite sides parallel. That's out of the definition, right? Both pairs of opposite sides are also what? Opposite sides are congruent. Both pairs of opposite sides are congruent. Both pairs of opposite angles are congruent. Consecutive angles are supplementary. Could they be congruent at some point? Yes. Okay. In squares and rectangles, they will be. Okay. And then diagonals bisect each other. Those 5 properties you need to commit to memory. Okay, because we're going to be using them over and over and over again throughout this chapter. Okay. We didn't see any examples here. Okay. But when you open up your homework is going to provide you something like this. It's going to say this is a parallelogram. So either through words they'll tell you it's a parallelogram or through notation. Okay, they might tell me something like that. And then they say this segment is 2a plus 12. And this one is a plus 14. And they ask you to solve for a. Well, this is just like anything else we've done in this entire course. We have a theorem that establishes a relationship, right? The theorem says in a parallelogram, opposite sides are what? Congruent. We now have 2 expressions and we get set equal each other, right? So I write the equation, 2a plus 12 equals a plus 14, and I go through and I solve it. Does that make sense? Okay? So as we move on through the course, you've seen a little bit of this already. In class, we establish the relationships. We look at why these relationships exist, and we prove them. But then when you get in your homework, you're applying that learned information to maybe an authentic or maybe a picture-type problem. Okay? So hopefully we understand that application is a high thinking skill, a high-level thinking skill. Okay? And that's the goal for us in tonight's homework, is to take these theorems and apply them inside some algebraic problems.
Did I do that algebra just completely wrong?
Let me pause this real quick and get back to you.